Welcome to part 3 of the SpaceGas video tutorial on bridge grillage analysis. Now we will get our model so that it's behaving correctly, that the members are bending about their respective major axes, and that our coordinate system is located at the centroid of the slab. So we have to move quite a few of these members. The slab itself is bending in its correct position. So let's consider then the longitudinal super T-beams. We need to try to estimate how much we need to move them in the negative Z direction so that the top of slabs is coincident. The way to do this is to go to the section properties, our super T, and to have a look at the cross section. So there's enough information on this to help us. The origin of the axis system shown here is the red dot, which is halfway between the extremities. So the y-axis ordinate here is 1380/2. The y-axis coordinate of the centroid of the section is given to us, and it's 175. The distance from the centroid to the middle of the slab is therefore 1380/2, this full distance, minus 175, and then minus half the depth of the slab. So this is 425 millimeters. So I'll turn off the render, I'll work in plan, I'll right click Super T's, and I'll scroll down to see the offsets. Make this a little bit bigger if it helps. dx, dy, dz at A and at B. A is the start node and B is the end node. We'll move the member in the negative Z direction. So minus 0.425 at both ends. And if we turn on the rendering and look at the isometric, we can see that we have shifted our super T sections down the right amount. Next, we must consider the edge beams. Currently, they're bending about their centroid, which is 255/2 or 127.5. We want them to bend about an axis that's 90 mil from their soffit. So the distance between the 90 mil bending axis and the 127.5 mil bending axis is 37.5. So I'll just right click on the edge beams to select them all. I'll scroll down and I'll move them down, so negative Z direction, by 37.5 millimeters. And I'll do this at both ends of the member. Press OK. If I look now, my model looks a lot better. I have a flat surface to my slab. But if I look at an elevation, I can see that my transverse end slabs are hanging over the end of my bridge. This isn't a problem because the bending takes place in the XY plane, so it won't affect the results, but it would be good for the rendering to see that the model conforms with our expectations. So I'll move to plan view. So I'll select my transverse end slab. And I want to move this in the positive X direction by half its length, or its planned dimension, which is 1400. So I want to move it 700 millimeters in the positive x direction. And if I pan to the other transverse end slab, this one I want to move in the negative x direction. And now my bridge looks as it should. All of the members are bending about the right or the correct axes. No members hanging over, so my model looks like a good representation of the bridge that we're trying to model. Next, I want to model the bending behavior of the slab in the transverse direction. Instead of, as it is right now, the model thinks it's bending between the center lines of the super T's. In fact, it's bending between the webs of the super T's. So we'll consider the proportion of the slab between the web of the super T and the center line of the super T to be rigid. And a way in SpaceGAS to achieve this is to put on member offsets. I'll select the members then that cross between the super T's. Go into my properties, and here I'll apply the offset. So I looking the y direction, and the distance between the center of the web and the center of the super T is 0.47. So I want to move the first node in the negative y and the second node in the positive y. So this looks about right. For the slabs then between the edge beams, here I want to move the first node only. Second node. And for these ones, it's the first node. So these offsets seem to correctly now model the width between the webs of the super T sections. I'll save my work. And next we want to assign supports. So I'll select the ends of the super T's here and apply a pin support. And I'll select the end here and apply a roller support. I can look at this in isometric. This looks good. And I can turn on and off the supports if I wish. Next, I want to validate that my model is behaving correctly. So I'll use a simple test loading case to check this. I'll select the nodes in the middle and I'll apply some point loads. We'll apply 100 kilonewtons downwards at each of these nodes. And we'll call it test load case. Look in isometric. This is certainly what I want it to look like. So I'll save. And carry out an analysis. First, I like to look at the deflected shape to see that it's behaving in a reasonable manner. And this certainly looks reasonable. And you can see also that the eccentricities of the members has been considered in the deflected shape. Next, we'll check the bending moments. And we want to examine the values. There are a lot of values on this, so it could be useful for us to only show the longitudinal members. To do this, we'll create a filter by section, and we'll select the edge and the super tees. I already have these selected. We'll call this longitudinal members. And then I can pick to have no filter or to only show those longitudinal members. So if we zoom in now, we can see that the bending moments are symmetrical. I have 2.43 on both edge beams, 1068 and 1068, 908, 908, and 883. I can turn off my loading if it interferes. The difference between these two values is carried by torsion in the transverse slab. We can see that these bending moments pass our check.